Hello everyone, my name is Jenny and I'm presenting our work on a backprojection-based deep image prior termed BP deep. In image restoration problems, the goal is recovering the original image X star having a corrupted image Y. This is often formulated as an optimization task of two terms, the data term and the prior. The data term forces the output image to comply with the observation model, while the prior poses an underlying assumption about the latent image. Our work is based on the Deep Image Prior paper published in 2018. Deep is an internal learning technique. It proposes a novel idea for using a deep neural network as a prior for image restoration tasks such as denoising in painting and more. The authors in Deep Image Prior claim that the structure of the CNN, the architecture itself, imposes a strong prior to the restoration problem. In the bottom line, Deep presents an idea in which a pre-trained network or an image dataset are never used. The only thing used in the restoration process is the corrupted image. The neural network is trained per image. The input to the network is Z, a random noise. The output of the CNN is X, the reconstructed image. AX is the reconstructed image after blur, and it is compared in the loss function to Y, the degraded blurred image. The CNN is optimized using gradient descent in order to generate prior of the blurred image. Notice that early stopping is required in order to prevent overfitting artifacts. Most of the papers that apply the approach of deep image prior use the typical LS loss function as appears here. They achieve rather limited performance and require a large number of iterations and test time. To mitigate this deficiency, we propose to use a BP loss function instead of the LS loss. The backprojection data term has been proposed recently, and it can be written in two ways, as displayed in this slide. The data term is designed for ill-posed problems, when the matrix A has less observations than unknowns. A dagger here is the pseudo-inverse of A, assuming the rows of A are linearly independent. We will apply this strategy to image deblurring. For deblurring, the BP loss can be implemented very efficiently using FFT. See our paper for the explicit FFT-based formula of the loss function. The performance of the deblurring process is compared between two cases, deep with BP loss and deep with LS loss. We use three different blur kernels, radial, Gaussian, and uniform, with three different noise levels, and add total variation to the loss function. These are the curves of PSNR versus iteration number for all 9 experiments. In green and blue, you can see the BP deep methods, and in red and pink, the LS deep. Few points are apparent when examining the curves. The first one is that with BP loss, deep yields higher PSNR. The second is that BP deep reaches its peak PSNR faster than LS deep. The third is that in most cases, adding the TV term improves the PSNR for both LS and BP. However, the bigger improvement is seen with BP deep. The last point is that early stopping is needed. Otherwise, the images are corrupted with noise. These are the final PSNR and SSIM results. It can be seen that BP deep is sensitive to noise. In low noise levels, when sigma is equal to square 0.3, BP displays best PSNR, and there is in fact no need in adding the TV term. However, when sigma is higher, BPTV presents the best PSNR out of the 4 methods. In general, when the noise level rises, the gap between BP and LS results reduces, and adding TV to the loss term usually boosts the results. These are some visual examples of the deblurring task using the 4 methods. Each row represents different kernel and noise level. It can be seen that fine details are more noticeable in the BP method, with and without TV. When using LS, the deblurred images are still blurry. In this work, we present the BP data term as an alternative to the LS data term for deep image prior. We present yet another evidence that untrained neural networks can reconstruct a sharp image using only its degraded version. We showed that using backprojection displays a significant improvement over the original deep work, both in reconstruction quality measures and in inference runtime. Finally, our code is available online. Feel free to check it.